The universe holds a monster that can swallow light itself. We call it a black hole. This is the story of the greatest cosmic mystery we have ever faced. By the end, you will journey across the event horizon and confront the wildest possibilities for what lies inside, from crushing singularities to gateways to other universes. We will explore how space and time shatter, whether information can truly vanish, and if reality itself might be a two-dimensional illusion. What do you believe awaits in that eternal dark? That boundary is known as the event horizon. It is the black hole's ultimate point of no return. Think of it as the edge of a cosmic waterfall, but one flowing downward into a bottomless pit of gravity. From the outside, you could still see the light from objects falling toward that edge, just as you can see a leaf drifting toward a waterfall's rim. But once something crosses that invisible line, it is gone forever. The gravitational pull becomes so overwhelmingly strong that the speed required to escape exceeds the speed of light itself. Since nothing in the universe can travel faster than light, nothing, not even a single photon, can ever climb back out. Crossing the event horizon is a one-way trip into a realm where the normal rules of physics as we know them cease to apply. It is a silent, invisible border separating the known universe from the absolute unknown. And for any object daring to cross it, the journey inward is about to become deeply strange, stretched into an impossibly long, thin strand in a process with a fittingly bizarre name, a fate we will return to soon. But what would crossing that horizon actually feel like? The experience is far more violent than a simple, silent slip into darkness. As you fall feet first toward the center, the black hole's gravity pulls on your feet more powerfully than it pulls on your head. This difference in force, known as a tidal force, is present everywhere, even on Earth, but it is so tiny we never notice it. Near a black hole, however, this gentle tug becomes a cosmic rack. The pull on your feet becomes unimaginably stronger than the pull on your head. You are not simply falling, you are being stretched. Your body would be elongated, pulled thinner and thinner like a piece of warm taffy. This bizarre and brutal process has a name that perfectly captures its essence: spaghettification. You would be stretched into a long, thin strand of atoms, a human noodle spiraling into the abyss. And this horrifying transformation would not even occur at the black hole's mysterious center. It would happen well before you reach the singularity, somewhere in the vast, empty space between the event horizon and the core. It is the black hole's way of announcing that the familiar laws of physics are no longer in charge. Your very atoms are being reorganized by forces beyond comprehension, a gruesome preview of the deeper chaos that lies ahead. This brutal stretching is merely the prelude. Beyond the event horizon, deep within that crushing darkness, lies the true enigma, the singularity. This is the theoretical heart of the black hole, the final destination of everything it consumes. According to our best equations, all the matter that falls in, every star, every planet, every stretched strand of atoms, is crushed and compressed into a single, unimaginable point. This point has zero volume. It occupies no physical space at all, yet it contains all the mass of the black hole. This means its density becomes infinite. The very concepts of here and there, of before and after, lose all meaning. Our understanding of the universe, built on the sturdy pillars of Einstein's theory of relativity, shatters completely at this point. The equations produce nonsensical answers, infinities that scream we have reached the limit of our knowledge. The singularity is not just an object, it is a boundary, a place where the map of physics ends and the territory of pure mystery begins. We are left with a profound question. Is this core truly a dimensionless point, a pinprick of infinite weirdness in the fabric of space? Or could it be something else entirely? A shape or structure our mathematics cannot yet describe. The answer may force us to rewrite the fundamental rules of reality. This is the great dilemma at the heart of the black hole. The singularity is not just a mystery, it is a screaming contradiction. Our most successful theory of the large-scale universe, Einstein's theory of general relativity, demands its existence. Relativity beautifully describes how mass warps the stage of space and time, creating the gravity that forms the black hole in the first place. But when it tries to describe the final result of all that warping, the equations point to this impossible, infinitely dense point. The theory predicts its own failure. It is as if you had a perfect map for navigating a continent, but when you finally reach the coastline, the map just shows a blank white space with the words, "Here there be monsters." The singularity is that blank space. It is where our map of reality tears. This clash becomes even more profound when we bring in our other great theory of reality, quantum mechanics. While relativity rules the cosmos, quantum mechanics governs the subatomic world. It is the rulebook for particles, probabilities, and the fuzzy, uncertain nature of the very small. And according to quantum law, information can never be truly destroyed. If you burn a book, the ashes and smoke still contain, in principle, the information needed to reconstruct every word. But a black hole with its singularity seems to be the ultimate information shredder. Everything that falls in is crushed into that dimensionless point, seemingly erased from the universe forever. This creates the famous black hole information paradox. Relativity says the information is gone, lost in the singularity. Quantum mechanics says that is absolutely forbidden. Both theories are spectacularly successful, yet they give us completely opposite answers about the most basic question of what happens to stuff inside a black hole. This fundamental conflict is not a minor scientific squabble. It is a glaring signal that we are missing a crucial piece of the puzzle. To resolve the paradox and finally understand the true nature of the singularity, we need a theory that can do the impossible, marry the colossal gravity of relativity with the quirky rules of the quantum world. Physicists call this the quest for a theory of quantum gravity. It would be a single framework that describes all forces, from the pull of a galaxy to the dance of particles, seamlessly. Finding it is arguably the greatest challenge in modern physics. The black hole's core, that terrifying singularity, is not just an endpoint. It is a cosmic laboratory, a natural experiment of extreme conditions that is actively challenging us to discover the next chapter in our understanding of the universe. The answer may not be a point at all, but something far stranger. Stephen Hawking realized this paradox presented a genuine crisis. He famously argued that black holes do not just trap matter, they should also slowly evaporate over astronomical timescales through a subtle quantum process. This evaporation would release a faint glow of radiation, now called Hawking radiation. But here was the problem. Hawking's calculations suggested this radiation was completely random, carrying no information about what fell in. If the black hole eventually evaporates entirely, leaving behind only this random radiation, then all the information about every star, planet, or person it ever consumed is permanently erased from the universe. This is not like burning a book to ashes. It is like burning a book and having the very laws of physics guarantee that the ashes bear no relationship whatsoever to the original text. The information is not scrambled, it is annihilated. For quantum physicists, this was an unthinkable violation. In their world, information is sacred. The universe is predictable in principle. If you know the complete state of a system now, the laws of physics should allow you to calculate its state in the past or the future. Information loss shatters this predictability. It means the universe has a permanent case of amnesia, and causality itself breaks down. The past becomes truly unknowable. Hawking's assertion ignited a decades-long debate, a war of ideas between the giants of relativity and quantum mechanics. It forced everyone to confront a terrifying possibility. Either our most cherished law of quantum mechanics was wrong, or our understanding of black holes was profoundly incomplete. This was not an abstract puzzle. The fate of information inside a black hole is a direct test of whether the universe is fundamentally orderly or ultimately chaotic. The resolution would require looking at the event horizon in a radical new way, not as a simple boundary, but as a dynamic surface holding a shocking secret. Hawking saw a way out of this crisis, a bridge between the quantum world and the colossal gravity of a black hole. His key insight was that space is never truly empty. Even in the deepest vacuum, at the tiniest scales, the universe is a seething quantum foam. Pairs of virtual particles, one of matter and one of antimatter, constantly flicker into existence, borrowing energy from the vacuum before almost instantly colliding and annihilating each other, paying back the energy loan. This strange quantum dance happens everywhere all the time, but place this quantum jitter right at the edge of a black hole's event horizon, and something extraordinary occurs. Imagine one of these particle pairs pops into being just at the precipice. In a freak accident of quantum chance, one particle falls across the event horizon while its partner escapes into space. The particle that falls in is lost forever, but the one that escapes carries real energy away from the black hole. To an outside observer, it appears as a faint thermal glow emanating from just outside the event horizon. This is Hawking radiation. It means black holes are not perfectly black. They have a temperature, and they are slowly leaking energy. Over timescales so vast they dwarf the current age of our universe, a black hole will radiate away all of its mass and simply vanish. Hawking had done the unthinkable. He used the quirky rules of the quantum world to prove that the most absolute objects predicted by relativity were not eternal after all. They could die. This was a monumental triumph of theoretical physics, a beautiful synthesis of two seemingly incompatible theories, but it came with a devastating cost. In Hawking's original calculation, the radiation escaping the black hole was purely thermal, like the glow from a hot stove. It contained no specific information about what fell in. It was random noise, so when the black hole finally evaporates, all the unique information about every star and atom it ever consumed would be lost to the cosmos forever, violating a core quantum law. Hawking had solved one paradox by creating an even deeper one. The battle lines were drawn, and the war for the soul of physics intensified. This paradox of disappearing information forced physicists to propose even wilder ideas. One of the most radical and controversial is the firewall hypothesis. Imagine you are finally crossing the event horizon, bracing for the strange stretching of spaghettification. But according to this idea, you would never get that far. Instead of a smooth passage into darkness, you would instantly smash into a blazing wall of unimaginable energy. This firewall, composed of ultra-high energy particles, would incinerate you and any information you carry long before you could experience the interior of the black hole. It sounds like science fiction, but it emerged from a desperate attempt to protect the sacred law of quantum mechanics. The logic goes like this. If Hawking radiation is to carry information out of the black hole, as many now believe it must, then something drastic has to happen at the event horizon to encode that information into the escaping particles. That encoding process, some argued, would require an enormous amount of energy, creating a literal wall of fire. The firewall would be the mechanism that saves information from being lost, but at a terrible cost. It shatters one of the foundational pillars of Einstein's general relativity, the equivalence principle. This principle states that if you are in free fall, like an astronaut floating in a spaceship with the engines off, you feel weightless. You cannot tell the difference between floating in deep space and falling freely toward a massive object like Earth, or even a black hole. There is no local experiment you could do to detect gravity's pull. The event horizon in Einstein's elegant picture is not a physical barrier. It is just a point in space you glide past without feeling a thing, until the tidal forces much later begin to pull you apart. The firewall completely violates this. An infalling observer would feel something catastrophic the instant they cross the horizon. They would not be weightless. They would be vaporized. This places the two great theories on a direct collision course. Quantum mechanics demanding information be preserved seems to require a firewall. General relativity, with its smooth geometry and equivalence principle, absolutely forbids it. You cannot have both. One of our most trusted descriptions of reality must be wrong at the most extreme edge of the cosmos. The firewall debate is not just about what is inside a black hole. It is a profound question about the nature of space and time themselves. Is the fabric of the universe truly smooth, or is it jagged and violent at its fundamental limits? The answer may lie not in thinking of the horizon as a place, but as a thing. The clash between a smooth horizon and a fiery wall forces us to ask a more fundamental question. What is the event horizon, really? Is it just a line in the sand drawn by gravity, or could it be something far more significant? This line of questioning leads us to one of the most revolutionary ideas in modern physics, the holographic principle. It proposes a truth so strange it sounds like philosophy. Everything we perceive as our three-dimensional reality, all the depth, the solidity, the space inside a volume, might be a grand illusion. The true information describing that reality could be painted like a cosmic fresco on its two-dimensional boundary. Think of the hologram on a credit card or a driver's license. It is a flat, shiny sticker, but when light hits it, it projects a seemingly three-dimensional image that floats in the air. The depth you see is not actually in the sticker. All the data needed to create that illusion of depth is encoded on that flat, two-dimensional surface. The holographic principle suggests our universe might work in a similar, though vastly more complex way. The three-dimensional space we live in, with its stars, planets, and people, could be a projection, and the data for that projection might reside on a distant, two-dimensional surface enclosing it. For a black hole, this idea becomes incredibly powerful. The interior of the black hole, that mysterious, three-dimensional volume containing the stretched matter and the enigmatic singularity, might not be the primary reality. Instead, all the information about everything that ever fell in could be perfectly preserved, not in the center, but smeared across its two-dimensional surface, the event horizon. Every atom, every bit of data from a swallowed star would be translated into incredibly tiny ripples and patterns on this spherical membrane. It would be like taking a complex three-dimensional sculpture and faithfully recording every single detail of it onto the surface of a balloon. The sculpture is gone, but a perfect representation of it exists on the skin. This solves the information paradox in an elegant, if utterly bizarre, way. Information is never lost inside the black hole because it never actually falls in. It is stored on the horizon. When Hawking radiation escapes, it is not random noise. It carries away little bits of that encoded information, slowly reading the data off the horizon like a cosmic scanner. The black hole evaporates, but the information is gradually and faithfully returned to the universe. There is no need for a destructive firewall because there is no traditional interior to fall into. The three-dimensional space inside the horizon is the illusion. The two-dimensional data on the surface is the reality. This principle does not just apply to black holes. Some theorists boldly suggest it could be true for the entire cosmos. That everything you see, feel, and experience, the vast three-dimensional theater of the universe, might be a holographic projection from a two-dimensional shell at the edge of everything. It is a staggering idea that redefines the nature of reality itself, suggesting that the deepest truths of the cosmos are written not in the volume of space, but on its skin. If the holographic principle bends our minds, the next idea threatens to snap them completely. It comes from string theory, the ambitious framework that attempts to be that unified theory of quantum gravity we desperately need. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but incredibly tiny, vibrating loops of energy called strings. The different vibrations of these strings give rise to all the particles and forces we see. From this perspective, a black hole is not a region of empty space warped around a singular point. It is a gigantic, tangled knot of these fundamental strings. This is the fuzzball proposal. Imagine taking all the mass and energy that formed the black hole, and instead of crushing it to a point, you let it settle into a vast, ball-shaped web of vibrating strings. This ball has a surface, and its surface is the event horizon. There is no empty interior, no smooth space to fall through, and most importantly, no singularity. The entire black hole, from its horizon to its core, is a solid, though fuzzy, object made of the fabric of spacetime itself. It is not a hole with a bottomless pit, but a densely packed star of pure stringy matter, fizzing with quantum activity at every point. The terrifying infinite density of the singularity is replaced by a very high but finite density spread throughout a large volume. The fuzzball is the black hole. This radical picture solves several problems at once. First, it banishes the mathematical nightmare of the singularity. No infinite densities, no breakdown of physics. The equations of string theory can potentially describe the fuzzball's entire structure without screaming in error. Second, it offers a stunningly simple solution to the information paradox. Remember the holographic principle stored information on the two-dimensional surface of the horizon. In the fuzzball model, that information is not just painted on the surface, it is the surface, and it fills the entire volume. Every bit of data from everything the black hole ever consumed is encoded in the specific, unique tangle of strings that make up that particular fuzzball. It is like a cosmic snowflake. No two are exactly alike. When Hawking radiation is emitted, it is not random thermal noise. It comes from the fizzing quantum activity on the fuzzball's surface, and that activity carries the distinct signature of the information stored within. Information is preserved naturally without needing firewalls or philosophical contortions. An astronaut falling toward a fuzzball would not experience a smooth passage into nothingness. They would not be spaghettified in empty space. Instead, they would simply collide with the fuzzball's surface, a boundary of immense but not infinite density, and become part of its stringy structure. The journey ends not at a dimensionless point, but at a physical wall of quantum threads. This model provides a complete, self-consistent picture from the outside in, built from the ground up by the proposed fundamental ingredients of reality. While still theoretical and fiercely debated, the fuzzball represents a powerful vision. It suggests that black holes are not the destroyers of physics, but its ultimate expression, revealing a universe woven not from points and voids, but from the vibrant, tangled threads of strings. But what if a black hole is not an end, but a beginning? Our journey through fuzzballs and firewalls has explored the nature of its interior, yet a more fantastic possibility lingers in the equations. Could the crushing core of a black hole be a tunnel to somewhere else? This idea is not pure fantasy. It emerges from the same mathematics that predicted black holes in the first place. When Albert Einstein and his colleague Nathan Rosen studied the solutions to the equations of general relativity, they found something astonishing. The theoretical map of a black hole's interior could mathematically be stitched to the map of a white hole's interior. A white hole is the theoretical opposite of a black hole, a region of spacetime where matter and energy can only erupt outward, never be entered. Connecting these two strange objects creates a bridge, a shortcut through the folded fabric of the universe. We call this an Einstein-Rosen bridge, but you likely know it by a more evocative name, a wormhole. Picture the universe not as a flat sheet, but as a vast, wrinkled bedsheet. To travel from one fold to another the long way, you would have to journey all across the fabric. But if you could pinch two distant folds together and puncture a hole through them, You would create a cosmic shortcut, a tunnel that bypasses the immense distance between those points. A wormhole is that tunnel. The entrance on one end would look and behave almost exactly like a black hole, a one-way door inward. The exit on the other end would be that white hole, violently spewing out whatever went in. In theory, this could connect not just different places, but different times or even different universes entirely. It is the ultimate gateway, promising journeys across the galaxy in an instant. The mathematics of general relativity allows for such a structure to exist. It is not a violation of the rules, but a bizarre consequence of them. However, there is a monumental catch. The wormholes described by Einstein and Rosen are catastrophically unstable. They are like a tunnel dug through wet sand. The moment it forms, the immense gravitational forces would cause it to pinch shut, to collapse faster than even a beam of light could traverse it. Any traveler entering would not emerge on the other side. They would simply hit the collapsing wall of the tunnel and be crushed, meeting a fate no different than at a traditional singularity. For a wormhole to be a practical shortcut, it would need scaffolding, something to prop it open against the relentless urge of gravity to slam it closed. This is where physics ventures into the realm of the speculative. Theorists propose that keeping a wormhole stable and traversable would require a substance with truly bizarre properties, something known as exotic matter. This is not just unusual matter like dark matter. Exotic matter, as defined here, would need to have negative mass or negative energy density. It would exert a kind of anti-gravity, a repulsive force that could push the walls of the wormhole apart and hold them open. While quantum physics allows for tiny amounts of negative energy to exist in certain circumstances, like in the Casimir effect, the amounts needed to stabilize a wormhole large enough for a person are astronomical and far beyond anything we know how to create or find. We have no evidence such material exists in usable quantities anywhere in the cosmos. So, could the black holes we observe in our universe actually be the mouths of wormholes? With our current understanding, almost certainly not. The black holes predicted by relativity and observed by our telescopes are in points. Their immense gravity leads to a singularity, or in newer models like the fuzzball, a dense quantum structure. There is no mathematical or observational reason to believe they secretly tunnel to another place. A natural wormhole would require conditions and materials that seem fantastically unlikely. Yet, the mere fact that such breathtaking shortcuts are not forbidden by our fundamental theory of gravity is profoundly significant. It tells us that the geometry of spacetime is far more malleable and strange than we ever imagined. Wormholes remain a powerful tool for thought experiments, pushing us to ask deeper questions about causality, connection, and the very structure of reality. They represent a dream written into the equations of the universe, a whisper that somewhere in the logic of spacetime, the idea of a doorway is waiting. If a black hole is a cosmic drain, then a white hole is its impossible fountain. This theoretical object is the exact mathematical opposite of everything we have explored so far. Where a black hole's event horizon is a one-way street inward, a white hole's horizon is a one-way street outward. Nothing can ever cross into a white hole from the outside. Instead, matter and energy can only erupt from its core, blasting out into the universe with unstoppable force. It is as if the universe itself had a safety valve, a point where space and time violently reverse their flow. Imagine trying to swim toward the center of a geyser as it erupts. The sheer outward pressure would repel you completely. That is the relentless nature of a white hole's boundary. While black holes are formed from the collapse of massive stars, white holes would have to be born from some unimaginable explosive birth, a singularity that expands instead of contracts, spewing out everything it contains in a single cataclysmic event. The equations of general relativity allow for such an object to exist. They are perfectly valid, symmetrical solutions, but that does not mean they are real. In all our observations of the cosmos, from radio telescopes to gravitational wave detectors, we have never seen anything that resembles a white hole. There are no unexplained, permanent cosmic eruptions with the gravitational signature of a massive object that nothing can enter. The universe seems to have a profound asymmetry. It readily creates black holes, but it appears to avoid creating white holes altogether. This leads to a compelling question: could the two be connected? Could the interior of a black hole in one part of the universe somehow link to the erupting throat of a white hole somewhere else or someone else? This idea gives rise to the concept of an Einstein-Rosen bridge, a wormhole. In this speculative picture, the black hole is not an endpoint but a passage. You fall through its event horizon, travel through a theoretical tunnel, and are violently expelled from the white hole on the other side. It is a complete cosmic plumbing system with a drain in one reality and a fountain in another. The mathematics suggests this tunnel would be catastrophically unstable, collapsing instantly. But the mere possibility written into the fabric of spacetime is tantalizing. It hints that a black hole's interior might not be a crushing prison, but a chaotic transit lounge. Yet without a single shred of evidence for a white hole's existence, this remains a beautiful piece of theoretical speculation, a ghost in the machine of the universe's equations. It shows us the limits of our maps. We can chart territories that are mathematically consistent, but which nature itself may have chosen never to build. So we are left with a universe full of dark drains and no sign of the fountains that might complete the circuit. But the strangeness of a black hole is not confined to its interior. Surrounding a spinning black hole is a region where the fabric of reality is wrenched into a vortex. This is the ergosphere, a cosmic maelstrom where space and time are not just curved but violently dragged. Picture a black hole not as a still drain, but as a whirlpool spinning at a significant fraction of the speed of light. This immense rotation does something extraordinary to spacetime itself. It twists the empty void around the black hole like thick honey being stirred by a colossal spoon. Outside the event horizon, but within this ergosphere, the dragging of space becomes so powerful that it overcomes the very structure of the cosmos. Here, an impossible rule takes hold. Nothing, absolutely nothing, can remain stationary. Even if you had a rocket engine with infinite power pointed directly away from the black hole, you could not stay in one place. You would be forced to move, to circle the black hole in the direction of its spin. It is not the black hole's gravity pulling you in at this point. It is space itself that is moving, and you are caught in its current. You are no longer an object moving through space. You are an object being carried by space. This bizarre effect has a startling consequence. It means that within the ergosphere, the concept of standing still loses all meaning. The universe itself is rotating around the black hole, and you are just along for the ride. This cosmic carousel is not just a curious spectacle, it is a potential power source of unimaginable scale. A brilliant physicist named Roger Penrose realized this whirling region of space could be exploited. He devised a purely theoretical, yet perfectly valid, method to steal energy from a rotating black hole. It is called the Penrose process. Imagine a brave, or perhaps foolish, astronaut ventures into the ergosphere with a large box of raw material. Once inside that zone of whirling space, they do not fight the current. Instead, they split the box into two pieces. With precise timing, they hurl one piece of the material backward against the direction of the spin. Because space is being dragged so fiercely, this backward thrown piece is given a kind of negative energy. It actually loses energy from the perspective of the universe outside. This loss is not free. The laws of physics demand balance. The other piece of the box, thrown forward with the spin, gains that lost energy and is catapulted out of the ergosphere at tremendous speed, carrying away more energy than the original box had when it entered. The black hole itself pays the price for this energy withdrawal. Its furious rotation slows down by a tiny, almost imperceptible amount. the astronaut has, in effect, mined the black hole's rotational energy. They have taken a piece of the vortex of spacetime and converted it into usable power. While this is a thought experiment far beyond our engineering, it reveals a profound truth. A black hole is not an isolated tomb. Its violent internal dynamics, the spin of its core, actively reshape the space around it, creating regions where the fundamental rules are rewritten and where energy, the very currency of the universe, can be theoretically harvested. The ergosphere shows us that the influence of a black hole extends far beyond its event horizon, turning the empty void into a cosmic dynamo. The vortex of the ergosphere is only a glimpse of the chaos within. If you were to survive the crossing and plunge past that whirling outer zone, you would encounter a reality far stranger than the static darkness of a simple black hole. The interior of a rotating black hole, described by the mathematics of physicist Roy Kerr, is not a quiet march toward a crushing point. It is a dynamic, turbulent landscape where the very architecture of space and time is torn apart and rewoven. Here, the fabled singularity, the endpoint of all paths, may not be a place at all, but a shape. Instead of a dimensionless point of infinite density, the Kerr solution suggests the core could be a ring. Picture not a dot, but a loop, a cosmic donut spinning at nearly the speed of light. This ring singularity is a tear in the fabric of reality, a one-dimensional circle where the known laws of physics dissolve. But unlike the point singularity, which is an inescapable wall, the ring presents a bizarre possibility. It is a hole not just in space, but in the rulebook of the universe. The equations imply that the space inside this spinning ring might not be filled with crushing gravity, but could be something else entirely, a region of negative space where the normal rules of gravity and geometry are inverted. This leads to a staggering theoretical proposition. If you could somehow navigate the violent tides and forces surrounding this whirling ring, and if you could align your trajectory perfectly through its center, you might not be destroyed. You might pass through the ring itself, and on the other side, the mathematics of the Kerr solution opens up into entirely new sets of coordinates, new regions of spacetime that are not part of our universe as we know it. One interpretation is that you would emerge into a different universe altogether, a separate cosmic bubble with its own laws and history. Another possibility is that the ring acts as a gateway to a distant part of our own universe, a wormhole without the need for exotic matter, naturally formed by the black hole's immense spin. You would not travel through a tunnel, but through a gravitational vortex that twists space into a shortcut. This is not a guaranteed exit. The region around the ring singularity is a chaotic storm of tidal forces and closed time-like curves where cause and effect could break down. It is perhaps the most unstable and dangerous environment conceivable. Yet, the mere mathematical possibility that a black hole could be a portal, not a prison, rewrites the final chapter of the journey. It suggests that at the heart of the greatest cosmic destroyer might lie a threshold, a spinning ring of fire that could be the ultimate door to elsewhere. This spinning ring of fire is not the only barrier within a rotating black hole. Deeper still lies a more subtle, yet perhaps more terrifying frontier known as the Cauchy horizon. Named for the mathematician Augustin Louis Cauchy, this is not a wall of rock or energy, but a boundary of knowledge. It is the point where the universe's ability to predict the future completely breaks down. To understand why, think about how physics works. If you know the exact state of a system right now, the position and motion of every particle, the laws of physics should allow you to calculate what it will do next. This predictability is the bedrock of science. The Cauchy horizon is where that bedrock crumbles into dust. It is an inner boundary, deeper than the event horizon, where the orderly equations that govern our reality simply stop giving clear answers. Beyond this line, the future becomes fundamentally unknowable, not because of our ignorance, but because the laws of physics themselves lose their predictive power. The map goes blank not from a lack of detail, but because the very concept of north and south ceases to exist. For an astronaut, falling through a rotating black hole crossing the Cauchy horizon would be the moment they leave the realm of predictable physics forever. And what awaits them in that lawless zone is the subject of fierce debate. One terrifying possibility is the blue sheet instability. As you approach this inner horizon, any radiation or energy falling in with you, even the faint echoes of starlight from the universe outside, would be caught in a catastrophic trap. The extreme warping of space and time would cause this energy to build up, not over millions of years, but in an instant from your perspective. The wavelengths of all that trapped radiation would be squeezed shorter and shorter, shifting to the blue end of the spectrum and concentrating into an unimaginable surge of energy. You would not simply cross a line, you would be hit by an infinite barrage of focused radiation, a wall of pure, concentrated fury that would annihilate any complex structure instantly. The Cauchy horizon would not be a gateway, but a cosmic shredder powered by the entire history of the universe shining down on you at once. Yet another, even stranger, possibility exists. Some mathematical models suggest that within the chaotic region near the Cauchy horizon, the fabric of spacetime could become so twisted that closed time-like curves form. These are paths through space and time that loop back on themselves. In such a place, you could theoretically travel in a circle and return to your own past. This is not time travel as we dream of it, with control and purpose. It is a catastrophic breakdown of cause and effect. The clear sequence of event A causing event B, which is the foundation of reality as we know it, would dissolve into nonsense. In this zone, an effect could precede its own cause. The universe would become a place of paradoxes where logic has no anchor. Whether you are vaporized by an infinite energy surge or lost in a maze of temporal paradoxes, the Cauchy horizon represents a deeper layer of mystery than the singularity itself. The singularity is where our equations fail by producing infinities. The Cauchy horizon is where our equations fail by offering too many possibilities, a smorgasbord of chaotic futures with no law to choose between them. It is the ultimate expression of the black hole's interior as a realm beyond prediction, a place where not just matter, but the very ordering principle of the cosmos is torn apart. The chaos of the Cauchy horizon hints at a deeper truth. To truly grasp what happens in the black hole's core, we must zoom in, far past planets and atoms, down to the very smallest possible size in the universe. This is the Planck scale, a realm so tiny it defies everyday intuition. If an atom were the size of our entire solar system, the Planck scale would be about the size of a single tree on Earth. At this unimaginably minute level, the smooth, continuous fabric of spacetime we take for granted ceases to exist. Instead, it becomes a seething, turbulent froth, a bubbling quantum foam. Picture the surface of a carbonated drink under a super-powered microscope, but instead of bubbles of gas, you are seeing bubbles of spacetime itself. In this quantum foam, the geometry of reality is not fixed. It is constantly fluctuating, churning with violent, random energy. Tiny wormholes, far smaller than an atom, spontaneously pinch into existence, connecting two random points in the foam before instantly snapping shut. Miniature universes might bubble up for a fleeting instant and then pop out of existence. Here, the concepts of here and there, before and after, lose all stable meaning. This is not empty space. This is space at its most fundamental, raw, and active state, a boiling pot where the ingredients of reality are perpetually being stirred. Under normal conditions, across the vast distances of the cosmos, this quantum fizz averages out into the smooth, calm stage upon which stars and galaxies perform. But inside a black hole, as you approach the crushing center, the gravitational forces become so overwhelmingly powerful that they magnify this microscopic frenzy. The quantum foam is no longer a hidden subatomic texture. It is stretched and energized, potentially becoming the dominant feature of reality. the smooth warping of spacetime predicted by general relativity gives way to a storm of quantum fluctuations. The singularity, then, might not be a neat geometric point or ring. It could be a maelstrom of this Planck-scale foam, a knot of spacetime so tangled and energetic that it represents a fundamental phase change in the nature of reality itself. In this view, matter is not crushed into a point, but dissolved and rewritten into the chaotic, bubbling foundation of the cosmos. The black hole's heart is not an end, but a transformation, where everything we understand as substance is unraveled back into the seething, probabilistic froth from which it may have first emerged. This quantum chaos forces us to confront a profound and unsettling truth about black holes. They may be the ultimate cosmic simplifiers. According to one of the most elegant ideas in theoretical physics, a black hole can be completely described with just 3 simple numbers. This is the essence of the no-hair theorem. The name is a metaphor. Hair in this context refers to any other distinguishing details, any unique features or complex information. The theorem states that a black hole has no hair. Once it forms and settles down, every single bit of its complex history is erased. All you need to know to predict its gravitational influence are 3 fundamental properties: its mass, its electric charge, and its angular momentum or spin. Think of it like describing a person. Instead of needing to know their life story, their memories, the color of their eyes, or the sound of their laugh, you are told only their weight, whether they carry a static charge, and how fast they are spinning. That is it. From the outside, a black hole formed from the collapse of a giant blue star with 10 planets is absolutely identical to a black hole formed from the collapse of a dense, old red star with no planets, provided they have the same mass, charge, and spin. All the intricate information about what made those stars unique, the composition of those planets, any complex structures that fell in later, is utterly lost to the external universe. The black hole presents a perfectly smooth, featureless facade defined solely by these 3 numbers. This stunning simplicity is a direct consequence of the extreme power of gravity. It is as if the black hole's event horizon acts as a cosmic blender and pressure cooker, taking a gourmet meal of countless ingredients, stars, gas, dust, even spacecraft, and reducing it all into a featureless puree. The output carries the total energy, the net spin, and the overall charge, but every recipe, every flavor, every detail of the original ingredients is gone. This is why the information paradox is so devastating. The no-hair theorem seems to provide mathematical proof that information is destroyed. If 2 black holes with the same mass, spin, and charge are completely indistinguishable, then the information about what formed them must be truly lost. There is no hidden barcode on the horizon, no secret fingerprint in the gravity field, at least not according to classical general relativity. The black hole is the simplest object in the universe, and in its simplicity, it commits the ultimate crime against quantum law. Yet, this very conflict is what drives the search for deeper answers. The holographic principle and the fuzzball concept are direct challenges to this classical view. They suggest the black hole is not simple at all. Its surface, or its entire interior, is a buzzing hive of quantum information, a complex system where every bit of data is preserved in a way we are only beginning to understand. The no-hair theorem, then, is not the final word. It is a brilliant description of the black hole as seen from a great distance through the lens of classical physics. But as we peer closer into the quantum storm at its horizon, we see the potential for hair after all, not in the smooth curvature of space, but in the microscopic, vibrating threads of reality itself. The theorem's beautiful simplicity may be an illusion, a shadow cast by a far more complex and hidden truth. Perhaps the singularity is not a flaw in our theories, but a sign we are looking for the wrong object entirely. Another radical idea proposes that what we call a black hole might be something else, a cosmic egg with a completely different interior. This is the gravastar, short for gravitational vacuum star. It is a theoretical object that matches a black hole in almost every way from the outside, yet banishes the nightmare of the singularity forever. Instead of an event horizon leading to a crushing point, a gravastar would have an unimaginably thin, yet indescribably strong shell. Picture a soap bubble, but one made of a material denser than anything in the universe, a membrane just a plank length thick. This shell would not be a point of no return, but a physical boundary you could, in theory, touch. Inside this shell, the story changes completely. The interior of a gravastar is not filled with warped space and falling matter. According to the model, it contains a void of pure dark energy. This is the same mysterious force thought to be accelerating the expansion of the entire cosmos, but here it is trapped inside a stellar-sized bubble. This dark energy exerts a powerful negative pressure, a kind of repulsive gravity pushing outward on the shell. The entire structure is a perfect balance, a cosmic standoff. The immense weight of the shell and all the matter it has collected pulls inward with incredible force, while the dark energy vacuum inside pushes outward with equal and opposite ferocity. This equilibrium is what prevents total collapse. There is no endless fall, no infinite density. The matter stops here at this ultimate wall. An astronaut falling toward a gravastar would not experience spaghettification in empty space. They would collide with this impervious shell and become part of it, adding their mass to the boundary, forever frozen just outside the inner void. From a great distance, a gravastar would be virtually indistinguishable from a black hole. It would warp light around it, creating a shadow. It would have a defining boundary from which light struggles to escape. But the crucial difference is that boundary is a real, physical surface, not a mathematical point of no return. This elegant idea solves the singularity problem by simply declaring it does not exist. The equations of general relativity are saved from their own embarrassing infinities because the collapse halts at the last possible moment, replaced by a phase of exotic dark energy. The information paradox, too, finds a potential resolution. Since nothing ever passes the shell into a singularity, all the information about what fell in remains preserved in the unique arrangement of the shell itself, like data etched onto the surface of an impossibly dense diamond. The gravastar is a compelling vision of cosmic restraint, suggesting that nature abhors a true infinity so much that it invents a new state of matter to avoid it. It is a universe that builds a final floor, a bottom to the bottomless pit. Gravity's ultimate monsters may hold a key to the universe's other great secrets. Beyond the event horizon, the mysteries of black holes could be intertwined with the two most profound puzzles in all of cosmology: dark matter and dark energy. We know these invisible forces dominate the cosmos. Dark matter is the unseen scaffolding that holds galaxies together with its gravitational glue, while dark energy is the mysterious force pushing the universe apart at an ever-increasing rate. We have never directly detected either one. They are ghosts in the cosmic machine, inferred only by their gravitational effects on the things we can see. But what if these ghosts are not entirely separate from black holes? What if they are two sides of the same impossible coin? One provocative idea suggests that dark matter, the universe's hidden mass, might not be made of exotic, unknown particles as many physicists suspect. Instead, it could be composed of countless black holes, but not the kind born from dying stars. These would be primordial black holes, hypothetical objects forged in the furnace of the Big Bang itself. In the first chaotic moments of the universe, random fluctuations in density could have been so intense that pockets of space simply collapsed directly into black holes. They could range in size from smaller than an atom to larger than a star, and they would have been scattered across the cosmos like seeds long before the first stars ignited. If vast numbers of these primordial black holes exist, drifting unseen through galactic halos, they would exert exactly the kind of gravitational pull we attribute to dark matter. They would tug on stars and bend light without emitting any of their own. We would not see them, but we would feel their weight. This elegant idea turns the mystery of dark matter into a census of ancient, invisible fossils from the birth of everything. Finding evidence for it, however, is a tremendous challenge, like searching for invisible needles in a cosmic haystack. Meanwhile, the puzzle of dark energy presents an even more radical possibility. Could the engine driving the universe's accelerated expansion be linked to the most powerful objects within it? Some theorists look toward the hearts of supermassive black holes, the giants that lurk in the center of nearly every galaxy, including our own Milky Way. These behemoths contain the mass of millions or even billions of suns compressed into a region smaller than our solar system. The conditions inside their cores are so extreme that they might be generating a form of vacuum energy, a repulsive force that could be leaking out and influencing the fabric of spacetime itself. In one speculative model, the interior of a black hole is not a singularity but a region of de Sitter space, the same kind of repulsive geometry that describes our dark energy-dominated universe. It is a mind-bending thought. The same force that tears the cosmos apart on the largest scales might be manufactured in the deepest pits of gravity. Perhaps every supermassive black hole is a tiny fountain of anti-gravity, and their combined influence across cosmic time contributes to the overall push we measure. These connections are, for now, the frontier of theoretical physics. They are not proven facts, but thrilling lines of inquiry that weave the story of black holes into the grandest narrative of all, the origin, structure, and ultimate fate of the entire universe. They suggest that by staring into the abyss, we might finally glimpse the hidden forces that shape everything we know. All these ideas are written in the language of mathematics, a map of possibilities. But maps need to be checked against the real territory. So what can we actually observe? The brutal truth is that we cannot see inside a black hole. No light, no signal, no information can escape from beyond the event horizon to tell us directly about singularities or fuzzballs. The interior is permanently veiled, yet we are not completely blind. We can study the black hole's shadow, the violent storms that rage just outside its point of no return. These observational clues are like listening to the roar of a waterfall from a distance. You cannot see the water at the bottom of the plunge, but the thunderous sound and the mist in the air tell you something immense is happening. For black holes, that roar comes in several forms. The first is the accretion disk. When a black hole pulls in gas from a companion star or a surrounding cloud, that material does not fall straight in. It spirals inward like water circling a drain, forming a flat, superheated disk of plasma. Friction and immense magnetic fields heat this disk to millions of degrees, causing it to glow fiercely across the electromagnetic spectrum, from X-rays to radio waves. By studying the light from these disks, astronomers can measure the black hole's mass and spin. The way the light flickers and dances tells a story of matter being stretched and compressed in the most extreme gravity possible, just outside the event horizon. Sometimes this process does more than just create a glowing disk. It can power the most energetic eruptions in the universe, relativistic jets. These are narrow beams of plasma shot out from the poles of a feeding black hole at nearly the speed of light. They can stretch for thousands of light years, punching through entire galaxies. The exact mechanism that launches these cosmic cannons is still debated, but it is thought to involve twisted magnetic fields anchored in the whirling accretion disk. The jet is a direct product of the black hole's ferocious spin and its ability to focus and accelerate matter with unbelievable efficiency. Observing these jets gives us a front-row seat to the raw power a black hole can wield over its surroundings. But perhaps the most revolutionary clue arrived in 2015, when scientists detected something that was once thought impossible to observe directly: gravitational waves. These are ripples in the fabric of spacetime itself, predicted by Einstein a century ago. They are created by the most violent events in the cosmos, like the merger of two black holes. When two black holes spiral inward and finally collide, they send a shudder through spacetime that travels across the universe. Our instruments, like LIGO and Virgo, are exquisitely tuned to catch these faint whispers. The signal is a chirp, a rapid increase in frequency and amplitude that ends abruptly. By analyzing this chirp, physicists can deduce the masses and spins of the black holes that created it. More importantly, the final moments of the merger and the ring-down that follows, where the new, larger black hole settles into a stable shape, provide a unique test of general relativity in the strongest possible gravity. The way the new black hole vibrates is like striking a bell. The tone it rings out depends entirely on its mass, spin, and crucially, the nature of its event horizon. Any deviation from the predicted tone could be a sign of something exotic, like a gravastar's hard surface or the fuzzy quantum structure of a fuzzball, instead of a perfect, smooth horizon. So while we may never receive a postcard from inside the abyss, the echoes of its violence, the glow of its last meal, and the ripples from its collisions are painting an increasingly detailed portrait of the monster at the edge of physics. The equations give us the map, but supercomputers let us take the journey. To peer into a place no telescope can ever see, scientists are building digital black holes. These are not simple animations, but full-scale universes in a box, governed by the precise mathematics of Einstein's general relativity. They run on some of the most powerful supercomputers on Earth, machines that perform quadrillions of calculations every second. The goal is to simulate the most violent and warped regions of spacetime, to watch what happens when matter crosses the event horizon, and to stress test our wildest theoretical ideas against the unforgiving logic of the code. It is physics by digital experiment. Researchers begin by defining the parameters of their virtual black hole, its mass, its spin, and what they want to throw into it. They then divide the surrounding space into a three-dimensional mesh of billions of points, a cosmic grid. At each point, the computer solves Einstein's fiendishly complex field equations, calculating how the presence of mass and energy warps the fabric of that grid. It is a monumental task, simulating the bending of reality itself, step by minuscule step. The result is a breathtaking visualization of gravity in action. We can watch as the smooth grid of space is stretched and twisted into a deep funnel around the black hole. We can follow a simulated star as it is torn apart by tidal forces, its gas stretching into a long streamer that spirals into the glowing accretion disk. Most importantly, we can send a virtual probe across the event horizon and see what the equations say happens next. Does it hit a seething firewall of energy right at the boundary? The simulations can model the quantum effects that might create such a barrier and see if it holds up or if it contradicts other known laws. Does it encounter a chaotic, stringy fuzzball instead of empty space? Theorists can program in the proposed properties of a fuzzball and watch how it interacts with infalling matter and radiates energy. These digital laboratories allow us to run experiments that are impossible in the real universe, to crash theories together and see which ones survive the collision. A simulation cannot tell us what is truly there, but it can reveal what is mathematically possible, or more often, what is mathematically impossible. It filters speculation through the rigid sieve of computation, showing us which beautiful ideas might actually work in the brutal reality of a black hole's heart. Every flash of light in these visualizations, every twist of the spacetime grid, is a direct translation of Einstein's genius into a form we can see and explore, a digital oracle whispering the secrets of the abyss. But these digital journeys reveal a possibility even stranger than a firewall or a fuzzball. A black hole might be the universe's most powerful time machine. This is not science fiction, but a direct consequence of Einstein's own equations. The extreme gravity near the event horizon does more than just trap light. It warps the very flow of time itself. Imagine two identical clocks perfectly synchronized. One stays on a spaceship far from the black hole. The other is placed on a probe and sent on a slow, careful descent toward the event horizon. To the crew on the ship watching through telescopes, something bizarre happens. As the probe gets closer to that invisible boundary, its clock appears to tick slower and slower. The hands move with agonizing lethargy. From the outside perspective, time for the infalling probe is stretching out, dilating. For the probe itself, its clock ticks normally. Its journey inward feels like it takes a reasonable amount of time, but by the time it reaches the event horizon from the ship's point of view, an eternity may have passed in the external universe. The crew would watch the probe freeze, its image reddening and fading, seemingly taking forever to actually cross the line. This is the ultimate expression of gravitational time dilation, an effect we measure with precise clocks on Earth, but magnified to an incredible extreme by the black hole's gravity. For the brave or foolish astronaut on that probe, a few minutes of descent could equate to thousands or even millions of years passing in the outside cosmos. They would, in a very real sense, travel into the universe's distant future in the blink of an eye. Stepping back from the brink would be impossible, but if they could, they would return to a world utterly transformed, where civilizations had risen and fallen, stars had died, and the galaxy was unrecognizable. The black hole becomes a one-way time capsule to the far future, yet this is only half the temporal weirdness. The mathematics of rotating black holes suggest an even more profound disruption of time might lurk within. Deep inside the chaotic zone near the Cauchy horizon, the twisting of spacetime could become so severe that it might create closed time-like curves. These are paths through the fabric of reality that loop back on themselves. In such a region, you could theoretically follow a trajectory that brings you back to the same point in space and at an earlier point in time. You would encounter your own past self. This is the theoretical foundation for travel into the past. It is not a journey you could control like a car on a highway, but more like being caught in a whirlpool that spins you backward through time. The implications are instantly paradoxical. What if you went back and prevented your own journey? The classic grandfather paradox emerges. If you travel to the past and stop your grandfather from meeting your grandmother, you would never be born, so you could never travel back to stop them. The logic collapses. Physics abhors such contradictions, which is why most physicists believe nature must prevent closed time-like curves from forming in reality. The laws of quantum mechanics or some yet unknown principle of causality preservation may act as cosmic censorship, ensuring these time loops are unstable or impossible to enter. The wild temporal warping might simply be a sign that our equations break down, not a blueprint for a time machine. So while a black hole can hurl you into the future, sending you to the past likely remains a forbidden fantasy, a ghost in the mathematics that the universe itself refuses to build. So the ultimate fate of matter inside a black hole remains a question with multiple competing answers. Each theory we have explored paints a different, vivid picture of that final destination. According to classical general relativity, the journey ends at the singularity. Every atom, every photon, every bit of information is crushed into an infinitely dense point. It is the ultimate compactor, reducing the complexity of a star to a single, featureless mathematical coordinate. In this view, matter is not transformed, it is terminated. Its unique identity is erased from the universe forever. The holographic principle offers a radical alternative. Here, matter is not destroyed but translated. As something falls through the event horizon, its three-dimensional structure is smeared and encoded onto the two-dimensional surface of the horizon itself. The physical object ceases to exist in any familiar form, but a perfect representation of it lives on, like a cosmic tattoo etched onto the black hole's skin. The matter becomes information, preserved in the microscopic ripples of spacetime at the boundary. The fuzzball model from string theory suggests preservation of a different kind. Matter is not crushed to a point nor painted on a surface, but woven into the fabric of the black hole itself. the infalling material becomes part of a vast, tangled ball of vibrating strings. Its information is not lost but distributed throughout the entire structure, defining the unique quantum state of that specific fuzzball. The matter is transformed, but its essence is stored in the intricate quantum memory of the strings. And then there is the quantum foam perspective, which sees the journey as a dissolution. As matter approaches the Planck-scale chaos at the center, it ceases to be matter at all. It unravels into the seething, probabilistic froth of spacetime itself. The distinction between the object and the stage it sits upon blurs and vanishes. The matter is recycled back into the raw, churning ingredients of reality. So which is it? Is the black hole a destroyer, a translator, a preserver, or a recycler? Our best physics gives us these compelling, yet contradictory, visions. The singularity screams destruction, the hologram whispers translation, the fuzzball hums with preservation. The quantum foam bubbles with dissolution. This is not a sign that science is failing. It is a sign that we are probing the very edge of understanding where our foundational theories clash. The fate of a single atom inside a black hole is now the central battlefield in our quest for a theory of everything. The answer will not just tell us what happens to stuff that falls in. It will reveal the deepest nature of information, spacetime, and reality itself. These cosmic monsters do more than just consume stars. They devour our most cherished assumptions about the universe. The struggle to understand what is inside a black hole is not merely a technical puzzle for physicists. It is a profound philosophical journey, forcing us to confront the very pillars of reality as we know it. First, consider space and time. We experience them as a stable, continuous stage, a four-dimensional fabric where events play out. But black holes reveal this stage is not rigid. It is a dynamic, malleable entity that can be stretched, twisted, torn, and perhaps even dissolved into a quantum foam. The event horizon is not a place in space, but a property of spacetime itself. Inside, the orderly distinction between space and time may utterly break down, with space becoming time-like and time becoming space-like. This shatters our intuition. We think of time as a river flowing in one direction, but near a black hole, that river can whirl into eddies and perhaps even loops. What we call reality's most basic structure is revealed to be contingent, flexible, and deeply strange under extreme conditions. Then there is the nature of information. In our daily lives, information is a pattern, the arrangement of atoms in a book, the sequence of bits on a hard drive. We believe it is durable, burn the book, and in principle, the smoke and ashes still hold a trace of the original text. The black hole information paradox challenges this at a cosmic level. Is information truly fundamental, a sacred ingredient the universe cannot destroy? Or is it merely an emergent property, a temporary pattern that gravity can ultimately erase? The fate of a single bit of data inside a black hole asks whether the cosmos is fundamentally predictable and orderly, or if true chaos and forgetting are possible. This is not just about physics, it touches on the nature of history, memory, and identity. If information can be lost, then the past is not fixed. It becomes blurry, unknowable. The universe could have a permanent case of amnesia. This leads directly to causality, the logical chain of cause and effect that makes reality coherent. Your childhood caused your adulthood. A struck match causes a flame. This principle is the bedrock of science and human experience. Yet, the theoretical possibility of closed time-like curves inside a rotating black hole threatens to snap this chain. If you can travel back to meet your younger self, which event is the cause and which is the effect, the paradoxes are immediate and mind-breaking. Most physicists believe nature must prevent this, that some law of cosmic censorship protects causality. But the fact that our best equations even allow for such possibilities tells us that the universe's commitment to a linear, sensible timeline might be a local rule, not a universal law. In the heart of a black hole, the story of the cosmos might not be written in a straight line. Ultimately, black holes hold up a mirror to the limits of human knowledge. We have built magnificent theories, general relativity and quantum mechanics that describe the cosmos with breathtaking accuracy. Yet they give us completely different, irreconcilable answers when pushed to the extreme. The singularity is not just a physical mystery, it is a symbol. It represents the edge of our map, the point where our tools of understanding fail. This is humbling but also exhilarating. It means reality is richer, more complex, and more mysterious than our current philosophies can contain. The black hole is a cosmic question mark, challenging us to invent new ways of seeing, to forge a theory that can marry the vast and the tiny. In seeking what is inside, we are not just exploring a distant object. We are probing the deepest nature of existence, space, time, and information, asking what is truly real and how much of it we can ever hope to know. From the silent boundary of the event horizon to the seething chaos of a quantum foam core, this journey has taken us through a landscape where reality itself is rewritten. We have confronted the classical nightmare of the singularity, a point of infinite density where physics ends. We have explored the radical possibility of the fuzzball, a black hole woven entirely from vibrating strings. We have considered the mind-bending holographic principle, where a three-dimensional interior is merely a projection from a two-dimensional surface. Each of these visions, from wormholes to white holes, from firewalls to gravastars, represents a brilliant attempt to map the unmappable. They are not just ideas, they are desperate, beautiful sketches of a territory we cannot see, drawn with the only tools we have, mathematics and imagination. And yet, the central question, what is truly inside a black hole, remains gloriously unanswered. It stands as one of the final frontiers in our understanding of the cosmos, a cosmic riddle that pits our two most successful theories against each other in a battle for the soul of physics. This is not a failure of science, it is its greatest promise. The unknown is not a void of ignorance, but a space filled with potential discoveries. Every observation of a black hole's shadow, every chirp of a gravitational wave, every line of code in a supercomputer simulation brings us a little closer to the truth. So stay curious, look up at the dark spaces between the stars and remember that within those voids lie the universe's most profound secrets, challenging us to think bigger, to question deeper, and to never stop wondering. Which of these incredible possibilities resonates most with you? Do you believe in the crushing singularity, the tangled fuzzball, or the cosmic hologram? Share your thoughts below, and if you hunger for more journeys to the edge of understanding, subscribe to explore the next great mystery